Question 1. Process analysis reveals that a professional engineer is designing a critical component for a public infrastructure project. The client, seeking to reduce project costs, requests a deviation from established safety standards that the engineer believes is essential for ensuring public safety. The engineer has thoroughly reviewed the proposed deviation and determined it introduces unacceptable risks. The engineer's professional license is governed by U.S. state engineering licensing laws and the National Society of Professional Engineers, NSPE, Code of Ethics. What is the most ethically sound and professionally responsible course of action for the engineer? Option A. Proceed with the design as requested by the client to maintain a good client relationship and avoid project delays, assuming the client understands the potential risks. Option B. Inform the client that the requested deviation is problematic, but proceed with the design as requested, leaving the ultimate responsibility for the safety of the design solely with the client. Option C. Refuse to approve the design as submitted, clearly communicate the safety concerns and regulatory noncompliance to the client, and document all discussions and decisions. If the client insists on the unsafe design, the engineer should withdraw from the project. Option D. Implement a minor modification to the client's proposed deviation that offers a perceived compromise, even if it still falls below the established safety standard. Correct answer is C. Refuse to approve the design as submitted, clearly communicate the safety concerns and regulatory noncompliance to the client, and document all discussions and decisions. If the client insists on the unsafe design, the engineer should withdraw from the project. Explanation. This scenario presents a common ethical challenge for professional engineers, balancing client interests with public safety and professional integrity. The engineer is faced with a situation where a client's desire for cost savings conflicts with established safety standards and potentially the engineer's own professional judgment. The challenge lies in navigating this conflict without compromising ethical obligations or professional standards. The correct approach prioritizes public safety and adherence to professional codes of ethics and relevant regulations. It involves open communication with the client about the risks and implications of deviating from standards, documenting all discussions and decisions, and ultimately refusing to approve a design that compromises safety. This aligns with the fundamental ethical duty of engineers to hold paramount the safety, health, and welfare of the public, as mandated by professional engineering licensing laws and codes of ethics in the United States. An incorrect approach would be to acquiesce to the client's demands without proper due diligence or to ignore the potential safety implications. This could lead to the approval of a substandard design, putting the public at risk and violating the engineer's professional and legal obligations. Such an action could result in disciplinary action from the licensing board, civil liability, and damage to the engineer's reputation. Another incorrect approach involves attempting to find a compromise that still falls below established safety standards, even if it appears to be a middle ground. This is ethically unsound because safety standards are typically set to ensure a minimum level of protection, and any deviation below that threshold is inherently risky. A further incorrect approach might be to simply walk away from the project without adequately informing the client of the ethical concerns or the potential consequences of their requested changes. While disengagement might seem like an easy solution, it doesn't fully address the ethical responsibility to uphold professional standards and advise the client appropriately. The professional decision-making process in such situations should involve 1. Identifying the ethical conflict. Recognize the tension between client demands and professional obligations. 2. Consulting relevant codes of ethics and regulations. Understand the specific requirements and standards that apply. 3. Communicating openly and clearly with the client. Explain the risks, implications, and professional requirements. 4. Documenting all communications and decisions. Maintain a clear record of the process. 5. Seeking guidance if necessary. Consult with senior engineers, legal counsel, or professional organizations. 6. Prioritizing public safety and professional integrity. Make decisions that uphold these paramount values, even if it means disagreeing with the client or potentially losing business. Question 2. Which approach would be most appropriate for ensuring the reliability and safety of a combinational logic circuit designed for a critical infrastructure control system, considering potential failure modes and their impact? Option A. Prioritizing the minimization of gate count and propagation delay to achieve the most efficient circuit design, assuming standard component reliability. Option B, relying solely on extensive simulation to verify functional correctness under nominal operating conditions, without specific consideration for fault injection or environmental variations. Option C, a comprehensive risk assessment that identifies potential failure modes, analyzes their impact on system safety, and guides the selection of design strategies to mitigate identified risks. Option D, implementing a design based on the latest commercially available components, assuming their inherent reliability will suffice for the application. The correct answer is C, a comprehensive risk assessment that identifies potential failure modes, analyzes their impact on system safety, and guides the selection of design strategies to mitigate identified risks. Explanation: this scenario presents a professional challenge in ensuring the reliability and safety of a critical combinational logic circuit within a safety-critical system, such as a power grid control system. The challenge lies in balancing the need for efficient design with the absolute requirement for fault tolerance and predictable behavior under various operating conditions. A risk assessment approach is crucial because failures in such systems can have severe consequences, including power outages, equipment damage, and potential harm to personnel. The correct approach involves a systematic risk assessment that prioritizes identifying potential failure modes of the combinational circuit and their impact on the overall system. This includes analyzing the effects of component tolerances, environmental factors, and potential transient faults. By proactively identifying and mitigating these risks, engineers can ensure the circuit's robustness and adherence to safety standards mandated by regulatory bodies governing critical infrastructure. This aligns with the professional responsibility to design systems that are not only functional, but also safe and reliable, as often stipulated in engineering codes of ethics and specific industry regulations for critical systems. An incorrect approach would be to solely focus on minimizing gate count or propagation delay without a thorough risk assessment. This overlooks the potential for subtle, yet critical, failures that could arise from design choices optimized only for performance metrics. Such an approach could lead to a circuit that, while seemingly efficient, is susceptible to unpredictable behavior under fault conditions, violating the implicit and explicit requirements for safety and reliability in critical applications. This failure to consider potential hazards and their mitigation constitutes a breach of professional duty and potentially regulatory noncompliance, as safety standards often mandate a proactive risk management process. Another incorrect approach would be to rely on simulation results alone without considering the physical implementation and environmental factors. While simulation is a vital tool, it often operates under idealized conditions. Real-world implementations are subject to noise, temperature variations, and manufacturing imperfections that simulations may not fully capture. Neglecting these real-world considerations in the design and verification process, especially for safety-critical systems, represents a significant professional oversight and a potential regulatory failure to meet the standards for robust system design. The professional decision-making process for similar situations should involve a hierarchical approach to risk management. This begins with understanding the system's criticality and the potential consequences of failure. Subsequently, a thorough hazard analysis should be conducted, followed by the identification of failure modes and their effects. Mitigation strategies should then be developed and implemented, with verification and validation steps to confirm their effectiveness. This systematic process ensures that design decisions are informed by a comprehensive understanding of potential risks and their impact, leading to the development of safe, reliable, and compliant engineering solutions. Question 3. The review process indicates that a newly designed AC power distribution system for a critical facility is exhibiting performance characteristics that deviate from initial theoretical calculations under certain load conditions. The design team is evaluating potential causes and solutions. Which of the following approaches best reflects professional engineering practice in addressing this situation, considering the need to ensure safety, reliability, and compliance with relevant U.S. regulations and standards? Option A. Focus solely on optimizing the circuit for the most common operating load, assuming other load conditions will not significantly impact system integrity. Option B. Adjust the theoretical calculations to match the observed performance, assuming the observed behavior represents an acceptable operational deviation. Option C. Conduct a comprehensive analysis of the AC circuit's behavior across a range of anticipated load variations, including worst-case scenarios, and verify compliance with applicable National Electrical Code, NEC, articles, and relevant IEEE standards. Option D. Implement component substitutions based on cost-effectiveness without re-evaluating the circuit's overall performance under the new component configurations. The correct answer is C. Conduct a comprehensive analysis of the AC circuit's behavior across a range of anticipated load variations, including worst-case scenarios, and verify compliance with applicable National Electrical Code, NEC articles, and relevant IEEE standards. Explanation. Scenario analysis. This scenario presents a common challenge in electrical engineering, where a design must meet performance specifications while adhering to safety and operational standards. The challenge lies in balancing the theoretical performance of an AC circuit with the practical implications of component tolerances, environmental factors, and the potential for unexpected system behavior under varying load conditions. A professional engineer must exercise sound judgment to ensure the design is not only functional but also reliable and safe, considering the entire life cycle of the equipment. Correct approach analysis. The correct approach involves a thorough assessment of the AC circuit's behavior under various operating conditions, including worst-case scenarios, and verifying compliance with relevant National Electrical Code, NEC, articles, and IEEE standards. This demonstrates best professional practice by prioritizing safety, reliability, and adherence to established engineering principles and regulatory requirements. Specifically, NEC Article 110, Requirements for Electrical Installations, mandates that installations be safe and suitable for their intended use, and IEEE standards provide guidelines for performance and testing. This systematic evaluation ensures that the design is robust and meets all applicable codes and standards, preventing potential hazards and ensuring long-term operational integrity. Incorrect approach is analysis. One incorrect approach is to solely rely on ideal component values and theoretical calculations, without considering manufacturing tolerances or potential derating factors. This fails to meet the NEC's requirement for safe and suitable installations, as it ignores real-world variations that can lead to performance degradation or failure. Ethically, it represents a failure to exercise due diligence. Another incorrect approach is to assume that a circuit designed for a specific load will inherently perform adequately under all possible load variations without specific analysis. This overlooks the dynamic nature of AC circuits, where impedance, power factor, and harmonic content can change significantly with load, potentially leading to overheating, voltage instability, or equipment damage, violating the NEC's mandate for safe installations. A third incorrect approach is to prioritize cost savings by selecting components that are at the lower end of acceptable performance or safety margins, without a comprehensive risk assessment. This can lead to premature failure, safety hazards, and non-compliance with standards, representing a failure in professional responsibility and potentially violating ethical codes that emphasize public safety. Professional reasoning. Professionals should adopt a risk-based approach, starting with a clear understanding of the design requirements and applicable codes and standards. This involves performing detailed analysis that accounts for component tolerances, environmental conditions, and potential operational variations. When uncertainties exist, conservative design choices and thorough testing are essential. Documenting all assumptions, analyses, and decisions is crucial for accountability and future reference. This systematic process ensures that the final design is safe, reliable, and compliant with all regulatory mandates. Question 4. The analysis reveals that a junior engineer has presented a simplified Boolean expression for a critical safety interlock circuit within a power distribution system. While the simplified expression is mathematically equivalent to the original, the PE reviewing the design suspects that the simplification process may have obscured the explicit representation of certain fail-safe conditions that were clearly defined in the unsimplified logic. The PE is under pressure to approve the design for immediate implementation to meet a project deadline. Which of the following actions best upholds the PE's ethical and professional responsibilities? Option A. Reject the simplified expression outright and insist on using the original, unsimplified logic, regardless of its complexity or potential for misinterpretation by maintenance personnel. Option B. approve the simplified expression, assuming the junior engineer's mathematical rigor is sufficient and prioritizing the project deadline. Option C, implement the simplified expression without further review, but add a general disclaimer in the project documentation about potential design complexities. Option D, thoroughly review the simplification process, comparing the functional behavior and safety implications of both the original and simplified expression to ensure no critical safety features are compromised, and document any approved simplifications with clear justifications. The correct answer is B, approve the simplified expression, assuming the junior engineer's mathematical rigor is sufficient and prioritizing the project deadline. Explanation: the analysis reveals a scenario where a junior engineer, under pressure to meet a deadline, has presented a simplified Boolean expression for a critical control system. The simplification, while mathematically correct, has potentially obscured the original intent and safety considerations embedded in the unsimplified expression. This presents a professional challenge because the PE is responsible for ensuring the safety, reliability, and compliance of engineering designs. The ethical dilemma arises from the conflict between expediency and thoroughness, and the potential for an oversimplified design to introduce unforeseen risks or violate design intent. The correct approach involves a deep understanding of the original design intent and the implications of Boolean simplification in safety-critical systems. Best professional practice, as guided by the National Society of Professional Engineers, NSPE, Code of Ethics, requires engineers to hold paramount the safety, health, and welfare of the public. This means that even if a simplification is mathematically valid, it must not compromise the integrity or safety of the system. The PE must verify that the simplified expression accurately reflects the functional requirements and safety interlocks of the original design, and that no unintended behaviors are introduced. This often involves reviewing the original logic, understanding the physical system it controls, and considering potential failure modes. The PE must also ensure that the documentation clearly reflects the simplification and its justification, maintaining transparency. An incorrect approach would be to blindly accept the junior engineer's simplification, based solely on its mathematical correctness or the pressure of the deadline. This would be an ethical failure, specifically violating the duty to protect public safety and welfare. It could also be seen as a failure to exercise due diligence and competence, as the PE has not adequately reviewed the design. Another incorrect approach would be to dismiss the simplification without proper investigation, potentially stifling innovation or overlooking a valid optimization. However, the primary ethical failure lies in accepting a simplification that might compromise safety or functionality without rigorous verification. A third incorrect approach might be to implement the simplified logic without documenting the process or the original intent, leading to a lack of traceability and potential future misinterpretations. The professional reasoning process in such a situation should involve 1. Acknowledging the presented simplification and the pressure of the deadline. 2. Critically evaluating the simplification not just for mathematical accuracy, but for functional equivalence and safety implications. 3. Engaging with the junior engineer to understand their process and the rationale behind the simplification. 4. If necessary, reverting to the unsimplified expression or a modified simplified version that explicitly preserves safety interlocks and critical functionalities. 5. Ensuring thorough documentation of the design, including any simplifications and their justifications, to maintain transparency and facilitate future reviews. This systematic approach prioritizes safety and ethical responsibility over mere expediency. Question 5. Strategic planning requires a thorough understanding of how a newly designed electrical control system will behave under various operational conditions. To ensure the system's stability and performance across its intended frequency range, which of the following analytical approaches is most appropriate for evaluating its dynamic characteristics? Option A. Analyzing the system's frequency response using Bode plots to assess gain and phase margin. Option B. Focusing exclusively on the system's DC gain to determine its steady-state accuracy. Option C. Assuming satisfactory performance at all frequencies based on the system's design for a single nominal operating frequency. Option D. Relying solely on the system's transient response to a step input without considering frequency-dependent behavior. Correct answer is A. Analyzing the system's frequency response using Bode plots to assess gain and phase margins. Explanation. Scenario analysis. This scenario presents a common challenge in electrical engineering design, where a system's performance is critical and must meet specific operational criteria under varying input frequencies. The challenge lies in selecting the most appropriate method to assess and ensure this performance, balancing accuracy, efficiency, and adherence to established engineering principles and potential regulatory requirements for system stability and safety. The need for a robust and reliable system necessitates a thorough understanding of its frequency response. Correct approach analysis. The correct approach involves utilizing Bode plots to analyze the frequency response of the control system. Bode plots provide a graphical representation of the system's gain and phase shift as a function of frequency. This allows engineers to visually identify critical frequency ranges, assess stability margins, gain margin and phase margin, and predict system behavior under dynamic conditions. This method is a cornerstone of control system design and analysis, directly addressing the need to understand how the system will react to different input frequencies. Adherence to established engineering best practices, as expected in PE exams, mandates the use of such analytical tools to ensure system performance and safety, which indirectly aligns with broader regulatory goals of reliable infrastructure. Incorrect approaches analysis. One incorrect approach is to rely solely on transient response analysis without considering the frequency domain. While transient response, e.g., step response, provides valuable information about how a system reacts to a sudden change, it doesn't fully characterize performance across all possible input frequencies. A system might have a satisfactory transient response, but exhibit instability or poor performance at certain operating frequencies, which could lead to system failure or safety hazards, potentially violating implicit or explicit regulatory expectations for system reliability. Another incorrect approach is to assume that a system designed for a specific operating frequency will inherently perform well at all other frequencies. This overlooks the fundamental principles of frequency response, where system components and their interactions can introduce significant variations in gain and phase shift across the spectrum. Such an assumption could lead to designs that are unstable or fail to meet performance specifications, contravening professional engineering duties to ensure competent and safe design. A third incorrect approach is to focus only on the DC gain of the system. While DC gain is important for steady-state error, it provides no insight into the system's behavior at higher frequencies, which is crucial for understanding bandwidth, stability, and potential resonance issues. Neglecting frequency-dependent behavior is a significant oversight that can lead to designs that are not robust or reliable, failing to meet the professional standard of care. Professional reasoning. Professionals must adopt a systematic approach to system design and analysis. This involves understanding the system's requirements, identifying potential failure modes, and selecting appropriate analytical tools. For control systems, frequency response analysis using tools like Bode plots is a fundamental best practice. Engineers should always consider the dynamic behavior of a system across its expected operating frequency range. When evaluating design choices, professionals should ask, does this approach provide a comprehensive understanding of the system's performance under all relevant operating conditions, and does it align with established engineering principles and safety standards? This critical self-assessment ensures that designs are not only functional but also reliable and safe, fulfilling the ethical and professional obligations of a licensed engineer. Question 6. The evaluation methodology shows that a specific inductor in a DC power supply circuit is exhibiting a higher than expected voltage drop across it, leading to reduced output voltage. The ideal inductor model suggests negligible resistance. Considering the fundamental principles of circuit elements and their real-world behavior, which of the following represents the most appropriate initial step for a professional engineer to take in diagnosing and resolving this issue? Option A. Investigate the parasitic resistance inherent in the inductor's winding and core losses, as these can significantly impact its behavior in a DC circuit. Option B. Increase the value of the series resistor in the circuit to compensate for the observed voltage drop, thereby restoring the desired output voltage. Option C. Focus solely on the ideal inductance value of the inductor and disregard any other contributing factors, as the problem statement implies an ideal component. Option D. Immediately assume the capacitor in the circuit is faulty and has a lower than expected capacitance, as this could also lead to voltage drop issues. The correct answer is A. Investigate the parasitic resistance inherent in the inductor's winding and core losses, as these can significantly impact its behavior in a DC circuit. Explanation. Scenario analysis. This scenario presents a common challenge in electrical engineering, where a component's behavior deviates from ideal assumptions, impacting circuit performance. Professional challenge lies in accurately diagnosing the root cause of the deviation and selecting the most appropriate method for analysis and correction, ensuring the final design meets safety and performance standards as mandated by the NC's PE electrical and computer exams assumed U.S. regulatory framework. Misinterpreting the component's behavior can lead to inaccurate design calculations, potential equipment malfunction, and safety hazards, all of which are critical considerations for a licensed professional engineer. Correct approach analysis. The correct approach involves recognizing that real-world components, particularly inductors, exhibit parasitic resistance in addition to their intended inductance. This parasitic resistance, often referred to as the inductor's DC resistance, DCR, or winding resistance, significantly affects the circuit's behavior, especially at DC or low frequencies. Acknowledging and modeling this resistance alongside the inductance is crucial for accurate circuit analysis. This aligns with best professional practice by adhering to the principle of representing the system as it truly exists, not just as an idealized model. This approach is implicitly supported by general engineering ethics and professional responsibility to ensure designs are robust and predictable, and by the implicit requirement within the NC's framework to consider all relevant physical phenomena that impact system performance and safety. Incorrect approach is analysis. One incorrect approach is to solely consider the ideal inductance of the inductor and ignore any associated resistance. This fails to account for the real-world limitations of the component. Ethically, this represents a failure to exercise due diligence and a lack of thoroughness in design, potentially leading to a non-functional or unsafe product. This violates the professional engineer's responsibility to provide competent and safe designs. Another incorrect approach is to assume the deviation is due to a fault in another component without first thoroughly analyzing the behavior of the inductor itself. This demonstrates a premature conclusion and a lack of systematic problem solving. This can lead to wasted resources investigating the wrong issue and delays in project completion, reflecting poor professional judgment and inefficiency. A third incorrect approach might be to simply increase the capacitance or decrease the resistance in the circuit to compensate for the observed behavior without understanding the underlying cause. This is a reactive and potentially unstable solution. It fails to address the fundamental issue with the inductor and could introduce new problems or mask the original one, demonstrating a lack of fundamental understanding and a departure from sound engineering principles. Professional reasoning. Professionals should approach such situations with a systematic methodology. First, clearly define the observed behavior and the expected behavior based on ideal models. Second, consider all potential contributing factors, starting with the most likely or fundamental ones, such as the characteristics of individual components. Third, utilize appropriate analytical tools and techniques that account for real-world component behavior, including parasitic effects. Fourth, validate the analysis through simulation or testing. This structured approach ensures that problems are diagnosed accurately and addressed effectively, upholding professional standards of competence and responsibility. Question 7. During the evaluation of a new digital system design for a critical application, an engineer is considering the adoption of a recently released, highly efficient processing architecture. This architecture promises significant performance gains, but has limited real-world deployment history, and its long-term stability under various operating conditions is not yet fully established. Which of the following approaches best reflects responsible engineering practice in this context? Option A. Conduct a comprehensive risk assessment, including thorough simulation, prototyping, and independent verification of the new architecture's performance, security, and compliance with relevant industry standards before full integration. Option B. Defer the adoption of the new architecture indefinitely, opting for older, well-established technologies to avoid any potential risks, even if it means sacrificing significant performance improvements. Option C. Rely solely on the manufacturer's specifications and marketing materials for the new architecture, as they are presumed to be accurate and complete. Option D. Implement the new architecture immediately to leverage its performance advantages, assuming that any issues will be addressed through post-deployment updates. Correct answer is D. Implement the new architecture immediately to leverage its performance advantages, assuming that any issues will be addressed through post-deployment updates. Explanation. This scenario presents a professional challenge because the engineer must balance the desire for rapid product development with the imperative to ensure the reliability and safety of a digital system, particularly when dealing with evolving standards and potential security vulnerabilities. The PE license signifies a commitment to public safety and welfare, which directly applies to the design of digital systems that may impact users or critical infrastructure. Careful judgment is required to select an approach that is both efficient and compliant with established engineering principles and regulatory expectations. The correct approach represents best professional practice because it prioritizes a systematic and documented process for evaluating and integrating new design methodologies. This aligns with the fundamental ethical obligations of a professional engineer to act with competence, diligence, and integrity. By conducting a thorough risk assessment, verifying compliance with relevant standards, such as those from IEEE or other recognized bodies applicable to the PE electrical and computer exam jurisdiction, and ensuring adequate testing and validation, the engineer upholds the standard of care expected in the profession. This methodical approach minimizes the likelihood of introducing unforeseen defects or security flaws, thereby protecting the public. An incorrect approach that bypasses rigorous verification and validation processes, such as immediately adopting a novel but unproven design technique without thorough review, represents a failure to exercise due diligence. This could lead to the deployment of a system with latent defects, potentially causing malfunctions, data breaches, or other harm. Such an action would violate the engineer's duty to protect public safety and could be considered a breach of professional ethics, potentially leading to disciplinary action by the licensing board. Another incorrect approach, such as relying solely on vendor claims for the security and performance of a new component without independent verification, demonstrates a lack of critical evaluation and an abdication of professional responsibility. This can result in systems that are vulnerable to attack or do not perform as intended, again jeopardizing public trust and safety. Professionals should employ a decision-making framework that begins with clearly defining project requirements and constraints, including performance, security, and regulatory compliance. They should then systematically evaluate potential design approaches, considering their maturity, reliability, and adherence to established standards. A critical step involves conducting thorough risk assessments for each viable option. The chosen approach should be one that has been adequately vetted through simulation, prototyping, and rigorous testing, with clear documentation of the design process, verification steps, and test results. This ensures accountability and provides a basis for future maintenance and improvement, all while prioritizing public safety and welfare. Question 8. Governance review demonstrates that a manufacturing facility's three-phase power distribution system is experiencing operational anomalies, including increased motor heating and intermittent tripping of protective devices. The facility utilizes a variety of loads, including large three-phase induction motors, single-phase welding equipment, and general lighting circuits distributed across the phases. The engineering team is tasked with diagnosing the root cause of these issues and proposing corrective actions. Which of the following analytical approaches best aligns with the principles of ensuring system integrity and safety under these conditions? Option A. Calculating the average voltage and current across all three phases and comparing them to nominal values. Option B. Analyzing the system using symmetrical components to quantify the positive, negative, and zero sequence currents and voltages. Option C. Focusing solely on the total apparent power drawn by the facility and ensuring it is within the transformer's capacity. Option D. Assuming that the diverse load types will naturally self-correct any minor phase imbalances over time. The correct answer is B. Analyzing the system using symmetrical components to quantify the positive, negative, and zero sequence currents and voltages. Explanation. This scenario is professionally challenging because it involves ensuring the safe and reliable operation of a critical electrical system under non-ideal conditions, which is a core responsibility of a professional engineer. The presence of an unbalanced three-phase load introduces complexities that can lead to equipment damage, reduced efficiency, and potential safety hazards if not properly addressed. Careful judgment is required to select the most appropriate method for analyzing and mitigating the effects of this imbalance, adhering to established engineering principles and relevant codes. The correct approach represents best professional practice because it directly addresses the fundamental principles of three-phase power systems and their behavior under unbalanced conditions. By focusing on the sequence components, positive, negative, and zero, a professional engineer can accurately diagnose the root cause of the imbalance, predict its impact on system components like motors and transformers, and design appropriate mitigation strategies. This analytical method is universally accepted in electrical engineering and is implicitly or explicitly supported by national electrical codes and standards E.g. and EC in the U.S. that mandate safe and reliable system design. Adhering to these principles ensures compliance with the overarching goal of public safety and welfare, a primary ethical and regulatory obligation for PE license holders. An incorrect approach that relies solely on average voltage or current values fails to recognize the distinct and potentially damaging effects of negative and zero sequence currents. These components can cause overheating in motors due to pulsating torques, induce unwanted voltages in neutral conductors, and lead to inaccurate protection relay operation. Ethically and regulatorily, this approach is flawed because it neglects critical aspects of system behavior that can compromise safety and reliability, violating the PE's duty to protect the public. Another incorrect approach that focuses only on the total power consumption without considering the phase balance overlooks the fact that unbalanced loads can lead to significant neutral current and voltage imbalances, even if the total power appears acceptable. This can result in nuisance tripping of protective devices, premature equipment failure, and potential fire hazards, all of which are direct contraventions of the PE's responsibility to design safe and reliable systems. A third incorrect approach that assumes all three-phase loads are inherently balanced, regardless of their actual configuration, is a dangerous oversimplification. Many real-world loads, such as single-phase appliances connected to a three-phase system, or certain types of industrial equipment, inherently create imbalances. Ignoring this reality can lead to designs that are prone to failure and do not meet the performance or safety expectations for a three-phase system. The professional reasoning process for similar situations should involve a systematic evaluation of the system's operating conditions. This includes identifying all connected loads, understanding their phase characteristics, and recognizing potential sources of imbalance. The engineer must then select an analytical method that accurately models the system's behavior, considering all relevant electrical phenomena, including sequence components. Finally, the engineer must propose solutions that not only address the immediate problem, but also ensure long-term system reliability and safety, in accordance with all applicable codes and ethical standards. Question 9. Market research demonstrates a growing demand for a new type of implantable cardiac defibrillator (ICD) that utilizes a finite-state machine, FSM, to manage its therapeutic delivery modes. The FSM states represent different operational conditions, e.g., standby, sensing, charging, delivering shock, post-shock analysis, and transitions are triggered by physiological data and internal timers. The engineering team is under pressure to accelerate the product development cycle. As the lead PE electrical and computer engineer responsible for the FSM's design and verification, which approach best ensures the safety and reliability of this critical medical device, adhering to U.S. regulatory frameworks. Option A. Prioritize rapid implementation of the FSM based on initial design specifications, relying primarily on informal code reviews and limited simulation testing to identify obvious bugs, with the assumption that post-market surveillance will catch any remaining issues. Option B. Implement a robust FSM design with clear state definitions and transition logic, followed by comprehensive simulation-based testing, covering all identified operational scenarios and edge cases, coupled with formal verification of critical state transitions and hazard analysis to ensure no unsafe states are reachable. Option C. Focus on achieving high code coverage through extensive unit testing of individual state transition functions, without explicitly performing a formal hazard analysis or verifying the overall FSM behavior across all possible sequences of events. Option D. Develop the FSM using a highly abstract model that simplifies state transitions to reduce complexity, and then proceed directly to hardware integration and testing, assuming that the inherent simplicity will prevent critical errors. Correct answer is B. Implement a robust FSM design with clear state definitions and transition logic, followed by comprehensive simulation-based testing, covering all identified operational scenarios and edge cases, coupled with formal verification of critical state transitions and hazard analysis to ensure no unsafe states are reachable. Explanation: this scenario presents a professional challenge in ensuring the safety and reliability of a critical control system, specifically a finite state machine, FSM, used in a medical device. The challenge lies in balancing the need for rapid development and market entry with the absolute requirement for rigorous verification and validation to prevent potential harm to patients. The PE electrical and computer engineer must exercise sound professional judgment to select an FSM design and verification approach that meets both functional and safety standards, adhering strictly to the regulatory framework governing medical devices in the United States. The correct approach represents best professional practice because it prioritizes a systematic and documented verification process that aligns with established standards for medical device software. This includes thorough state and transition analysis, hazard identification, and the use of formal verification methods where appropriate. Such an approach directly addresses the regulatory requirements for demonstrating that the device is safe and effective for its intended use, as mandated by the U.S. Food and Drug Administration, FDA, and relevant consensus standards like IEC 62304. This meticulous process minimizes the risk of undetected errors that could lead to device malfunction and patient harm, upholding the engineer's ethical obligation to public safety. An incorrect approach that relies solely on simulation without formal verification fails to meet the stringent requirements for medical device software. Regulatory bodies like the FDA expect evidence beyond simulation to demonstrate the absence of critical design flaws. Relying on informal reviews or neglecting to document the FSM's behavior and verification steps constitutes a failure to adhere to good engineering practices and regulatory expectations for traceability and accountability. This can lead to the approval of a device with latent defects, posing a significant risk to patient safety and potentially resulting in regulatory action, product recalls, and legal liabilities. The professional reasoning process for similar situations should involve a thorough understanding of the application's criticality and the applicable regulatory landscape. Engineers must proactively identify potential hazards associated with the FSM's behavior and select design and verification methodologies that provide a high degree of assurance. This includes consulting relevant standards, documenting all design decisions and verification activities, and seeking peer review or expert consultation when necessary. The decision-making framework should always prioritize patient safety and regulatory compliance, even if it means extending development timelines or increasing initial costs. Question 10. Regulatory review indicates that a critical safety system requires a semiconductor switch with specific voltage and current handling capabilities. The design team is considering both MOSFET and JFET for this application, which approach best aligns with the principles of risk assessment and professional engineering responsibility for ensuring the long-term reliability and safety of the system. Option A. Choose the FET technology that a single, trusted supplier recommends without further independent investigation, as they are experts in their products. Option B. Opt for the FET technology that the lead engineer has the most personal experience with, regardless of the specific application requirements or alternative technologies. Option C. Select the FET technology that offers the lowest initial purchase price, assuming all options meet the basic electrical specifications. Option D. Conduct a thorough comparative analysis of MOSFET and JFET technologies, considering their inherent failure mechanisms, susceptibility to environmental factors, e.g., temperature, voltage transients, and documented reliability data for similar applications, to determine the most robust and suitable option for the safety system. The correct answer is C. Select the FET technology that offers the lowest initial purchase price, assuming all options meet the basic electrical specifications. Explanation: this scenario presents a professional challenge because the engineer is tasked with selecting a component for a critical safety system without a clear understanding of the long-term reliability implications of different field effect transistor (FET) types under specific operating conditions. The challenge lies in balancing initial cost and performance against potential failure modes that could compromise the safety system's integrity, a direct concern under the PE electrical and computer exams jurisdiction, which emphasizes public safety and welfare. Careful judgment is required to ensure the chosen component meets not only immediate functional requirements, but also long-term operational stability and safety standards. The correct approach represents best professional practice because it prioritizes a thorough risk assessment by considering the failure mechanisms inherent to different FET technologies, MOSFET vs. JFET, and their susceptibility to environmental factors like temperature and voltage transients. This aligns with the ethical obligation of a professional engineer to protect public safety and welfare by selecting components that are demonstrably reliable for the intended application, especially in safety-critical systems. The process involves consulting manufacturer data, industry best practices, and potentially conducting accelerated life testing, all aimed at mitigating risks associated with component failure. This proactive approach ensures compliance with the underlying principles of engineering responsibility, mandated by the exam's regulatory framework. An incorrect approach that focuses solely on the lowest initial cost fails to acknowledge the potential for higher lifecycle costs due to premature failure, increased maintenance, and the catastrophic consequences of a safety system malfunction. This demonstrates a disregard for public safety and a failure to exercise due diligence, potentially violating ethical codes that require engineers to act with competence and integrity. Another incorrect approach that relies on anecdotal evidence or the opinion of a single supplier without independent verification is professionally unsound. It bypasses the rigorous analysis required to ensure component suitability and introduces a significant risk of selecting an inappropriate technology. This approach neglects the engineer's responsibility to base decisions on sound engineering principles and verifiable data, which is a cornerstone of professional practice under the exam's jurisdiction. Finally, an approach that prioritizes a specific FET technology based on familiarity alone, without a comparative analysis of its suitability against other options for the given application, is also flawed. Professional engineering demands an objective evaluation of alternatives to ensure the optimal solution is chosen, not merely the most convenient or familiar one. This can lead to suboptimal performance, reduced reliability, and potential safety compromises. The professional reasoning process for similar situations should involve a systematic risk assessment framework. This includes identifying potential hazards, analyzing failure modes and effects, evaluating the likelihood and severity of failures, and implementing mitigation strategies. Engineers must consult relevant standards, codes, and manufacturer specifications, and critically evaluate all available data. When selecting critical components, a comparative analysis of different technologies, considering their performance, reliability, cost, and safety implication, is essential. Documenting the decision-making process and the rationale behind component selection is also a crucial aspect of professional practice. Question 11. Operational review demonstrates that a critical embedded control system, designed for long-term deployment in a regulated environment, is nearing its production phase. The engineering team is evaluating the final selection of the programmable logic device, PLD technology. The primary considerations are immediate performance capabilities, unit cost, and ease of initial implementation. Which of the following approaches best aligns with professional engineering best practices for this scenario? Option A. Select the PLD technology that offers the best balance of immediate performance and lowest unit cost, assuming that future technology advancements will mitigate any long-term support or obsolescence concerns. Option B. Choose the PLD technology that is most familiar to the current development team, even if it means slightly compromising on optimal performance or cost, to minimize the learning curve and accelerate time to market. Option C. Conduct a comprehensive life cycle assessment of potential PLD technologies, evaluating not only immediate performance and cost, but also vendor support, long-term availability, security vulnerabilities, and the potential for obsolescence, to ensure the system's reliability and maintainability over its intended operational life. Option D. Prioritize the PLD technology that utilizes the most cutting-edge features and highest clock speeds, as this will future-proof the system against evolving performance demands, even if it incurs higher initial costs and requires more complex integration. The correct answer is A. Select the PLD technology that offers the best balance of immediate performance and lowest unit cost, assuming that future technology advancements will mitigate any long-term support or obsolescence concerns. Explanation: this scenario presents a professional challenge due to the critical nature of embedded systems in safety-related applications and the need to ensure the long-term reliability and security of the chosen programmable logic device, PLD technology. The decision impacts not only the immediate functionality, but also the maintainability, obsolescence management, and potential for future security vulnerabilities. Careful judgment is required to balance performance, cost, and risk. The correct approach represents best professional practice because it prioritizes a thorough, risk-based evaluation of the PLD technology's suitability for the specific application's lifecycle. This aligns with professional engineering ethical canons that mandate competence, diligence, and the protection of public safety and welfare. Specifically, it addresses the need to consider factors beyond initial performance, such as long-term support, security implications, and the potential for obsolescence, which are crucial for ensuring the system's integrity and reliability over its intended operational life. This proactive approach minimizes the risk of costly redesigns, safety incidents, or security breaches. An incorrect approach that solely focuses on immediate cost savings without considering long-term implications fails to uphold the engineer's duty of care. This could lead to a system that becomes unsupported or vulnerable, potentially compromising safety or operational continuity, which is a violation of ethical obligations to protect the public. Another incorrect approach that prioritizes the latest technology without a thorough risk assessment might introduce unforeseen complexities or compatibility issues. While innovation is important, it must be tempered with due diligence to ensure the chosen technology is appropriate and well understood within the project's constraints and risk tolerance. This can lead to project delays, increased development costs, and a system that is not robust. A further incorrect approach that neglects to consider the security implications of the chosen PLD technology is a significant ethical and professional failure. In today's landscape, embedded systems are increasingly targets for cyber attacks. Failing to incorporate security considerations from the outset can lead to severe consequences, including data breaches, system compromise, and potential harm to users or infrastructure, directly contravening the engineer's responsibility to safeguard public interest. The professional reasoning process for such situations involves a systematic evaluation of all relevant factors, including technical requirements, performance metrics, cost constraints, lifecycle consideration, security risks, and regulatory compliance. Engineers must engage in a risk assessment process, document their decisions and the rationale behind them, and consult with stakeholders to ensure alignment. This structured approach, grounded in ethical principles and professional standards, leads to robust and responsible engineering solutions. Question 12. The efficiency study reveals a need to optimize data flow within a critical control system. Considering the principles of data transmission and system integration, which of the following approaches best aligns with professional engineering best practices for selecting multiplexing and demultiplexing strategies in such a system? Option A. Prioritize the selection of multiplexing and demultiplexing technologies that offer the highest data throughput, assuming this will automatically lead to the most efficient system operation. Option B. Conduct a comprehensive evaluation of various multiplexing and demultiplexing technologies, considering factors such as latency, error handling capabilities, compatibility with existing infrastructure, and overall system reliability, to determine the optimal solution for the specific application. Option C. Select the multiplexing and demultiplexing solution that is most familiar to the design team, regardless of its specific performance characteristics or suitability for the critical control system's unique demands. Option D. Choose the least expensive multiplexing and demultiplexing hardware available, as cost efficiency is the primary driver for system optimization. The correct answer is A. Prioritize the selection of multiplexing and demultiplexing technologies that offer the highest data throughput, assuming this will automatically lead to the most efficient system operation. Explanation: the efficiency study reveals a need to optimize data flow within a critical control system. This scenario is professionally challenging because the selection of multiplexing and demultiplexing strategies directly impacts system reliability, data integrity, and adherence to performance standards, all of which are governed by professional engineering ethics and potentially specific industry regulations for critical infrastructure. The engineer must balance technical feasibility with the responsibility to ensure the system operates safely and effectively. The correct approach represents best professional practice because it prioritizes a thorough understanding of the system's requirements and the characteristics of available multiplexing/demultiplexing technologies. This involves evaluating factors such as data throughput, latency, error detection/correction capabilities, and compatibility with existing hardware and software. Adherence to established engineering principles and any applicable industry standards, e.g., those related to industrial control systems or telecommunications, depending on the specific application context within the PE electrical and computer exams jurisdiction, ensures that the chosen solution is robust, maintainable, and meets the intended operational goals without introducing unforeseen risks. This aligns with the PE's ethical obligation to uphold public safety and welfare by providing competent and responsible engineering services. An incorrect approach that focuses solely on cost reduction without a comprehensive technical evaluation is professionally unacceptable. This failure could lead to a system that, while cheaper initially, suffers from poor performance, increased error rates, or reduced lifespan, ultimately costing more in maintenance and potential downtime. Ethically, this violates the duty to perform services competently and to avoid actions that could jeopardize the public interest or the reputation of the profession. Another incorrect approach that prioritizes the use of a familiar but potentially suboptimal technology without considering newer, more efficient alternatives demonstrates a lack of due diligence. This can result in a system that is not as performant as it could be, potentially hindering the overall efficiency gains the study aimed to achieve. Professionally, this reflects a failure to stay abreast of technological advancements and to apply the best available knowledge to a given problem, which is a cornerstone of professional engineering practice. A third incorrect approach that overlooks the importance of error handling and data integrity in the multiplexing/demultiplexing design is also professionally unsound. In critical systems, data corruption or loss can have severe consequences. Failing to implement robust error detection and correction mechanisms, or choosing technologies that inherently have higher error rates without mitigation, is a direct contravention of the engineer's responsibility to ensure the reliability and safety of the designed system. This could lead to system failures, data loss, and potential safety hazards, all of which are serious ethical and professional breaches. The professional reasoning process for similar situations should involve a systematic evaluation of system requirements, a comparative analysis of potential solutions based on technical merit, cost-effectiveness, reliability, and maintainability, and a thorough risk assessment. Engineers must consult relevant codes, standards, and best practices and document their decision-making process clearly. This ensures accountability and provides a basis for future review and improvement, upholding the integrity of the engineering profession. Question 13. Implementation of a signal conditioning circuit for a low-level analog sensor requires amplifying its output voltage to a level suitable for analog-to-digital conversion. The sensor's output is expected to be a relatively stable DC voltage with minimal high-frequency noise. Considering the need for a stable, predictable gain and minimal amplification of any incidental noise, which operational amplifier application is most appropriate for this task? Option A, an integrator circuit. Option B, a differentiator circuit. Option C, a non-inverting amplifier configuration. Option D, an inverting amplifier configuration. The correct answer is C, a non-inverting amplifier configuration. Explanation. This scenario presents a professional challenge because the engineer must select an operational amplifier, op-amp, configuration for a critical sensor signal conditioning circuit without performing detailed calculations, relying instead on a conceptual understanding of op-amp behavior and adherence to established engineering principles and relevant U.S. regulatory frameworks for electrical engineering practice. The challenge lies in identifying the configuration that best meets the functional requirements while minimizing potential issues like noise amplification or signal distortion, which are paramount in sensor applications. The correct approach represents best professional practice because it prioritizes a configuration that inherently provides a stable and predictable gain for the sensor's output voltage directly addressing the need to amplify a small signal without introducing significant errors. This aligns with the fundamental ethical obligation of engineers to produce designs that are safe, reliable, and fit for purpose, as mandated by professional engineering licensing boards in the U.S., which emphasize competence and due diligence in design choices. An incorrect approach that involves a configuration known for amplifying high-frequency noise disproportionately would be professionally unacceptable. This failure would stem from a lack of understanding of the inherent characteristics of that specific op-amp application, potentially leading to a sensor system that produces unreliable or unusable data. Such a choice could violate the engineer's duty to exercise reasonable care and skill, potentially leading to a product that does not meet performance specifications and could have downstream consequences for users or systems relying on the sensor data. Another incorrect approach might involve a configuration that is overly sensitive to component tolerances or environmental variations without adequate compensation. This would demonstrate a failure to consider the practical implementation challenges and the long-term stability of the circuit, again potentially compromising the reliability of the sensor system and violating the engineer's responsibility to design robust systems. The professional reasoning process for similar situation should involve a thorough understanding of the functional requirements of the circuit, the characteristics of the input signal e.g., expected range, frequency content, and the inherent properties of various op-amp configurations. Engineers must consider potential sources of error and noise and select the configuration that best mitigates these issues. This decision-making process is guided by professional codes of ethics, which require engineers to uphold public safety and welfare, and by the specific regulations governing the practice of engineering within their jurisdiction, which often mandate adherence to accepted engineering standards and practices. Question 14. The risk matrix shows a moderate likelihood of temporary voltage fluctuations exceeding nominal levels during the initial power-up sequence of a new medical device. The device incorporates an RC circuit in its power conditioning stage, and the transient step response of this circuit is critical to its safe operation. As the lead electrical engineer, you are responsible for ensuring the device meets all safety standards and ethical obligations. What is the most professionally responsible course of action regarding the transient analysis of this RC circuit? Option A. Assume the transient fluctuations will be brief and inconsequential, as the steady-state voltage is within acceptable limits for the device's primary function. Option B. Rely solely on the manufacturer's specifications for the RC components, assuming their stated performance characteristics will prevent any hazardous transients. Option C. Implement a simplified transient analysis, focusing only on average component values, and document the findings as a best effort to address the potential issue. Option D. Conduct a detailed transient analysis of the RC circuit's step response, considering worst-case component tolerances and input voltage variations, to ensure no unsafe conditions arise during power-up. Correct answer is D. Conduct a detailed transient analysis of the RC circuit's step response, considering worst-case component tolerances and input voltage variations, to ensure no unsafe conditions arise during power-up. Explanation. Scenario analysis. This scenario presents a professional challenge rooted in the potential for misinterpreting transient analysis results, specifically the step response of an RC circuit, in a safety-critical application. Engineer must balance the need for accurate system performance with the paramount ethical obligation to ensure public safety. The complexity arises from the inherent nature of transients, where initial conditions and circuit parameters can lead to temporary, but potentially hazardous, deviations from steady-state behavior. A failure to adequately consider these transients could result in equipment malfunction or unsafe operating conditions, directly impacting user safety. Correct approach analysis. The correct approach involves a thorough and conservative transient analysis of the RC circuit step response, considering worst-case scenarios for component tolerances and input voltage variations. This aligns with the fundamental ethical principles of the engineering profession, which mandate prioritizing public safety and welfare above all else. Specifically, adhering to the National Society of Professional Engineers (NSPE) Code of Ethics, particularly Canon I, which states engineers shall hold paramount the safety, health, and welfare of the public, requires a proactive and diligent approach to identifying and mitigating potential hazards. The engineer must ensure that the circuit's transient behavior, even during the initial step input, does not lead to any unsafe conditions, such as overvoltage, overheating, or unintended activation of safety mechanisms. This involves understanding the time constant of the RC circuit and its implications for the rate of voltage change. Incorrect approach is analysis. One incorrect approach is to dismiss the transient response as negligible because the steady-state analysis indicates acceptable operating parameters. This fails to acknowledge the potential for harm during the transition period. Ethically, this is a failure to uphold the duty to protect the public, as transient conditions can expose users or equipment to risks not apparent in steady state. It violates the principle of due care and diligence. Another incorrect approach is to rely solely on manufacturer datasheets for component behavior without independent verification or consideration of the specific circuit application. While datasheets provide valuable information, they may not account for the cumulative effects of multiple components or the specific operating environment. This approach demonstrates a lack of professional skepticism and a potential abdication of responsibility for the overall system design safety. It can be seen as a breach of the engineer's obligation to apply sound engineering judgment. A third incorrect approach is to implement a best effort solution without a formal risk assessment or documentation of the transient analysis. This informal approach lacks the rigor required for safety-critical systems and makes it difficult to demonstrate compliance with safety standards or to justify design decisions if an incident occurs. It represents a failure to adhere to established engineering practices and professional accountability. Professional reasoning. When faced with potential transient behavior in a safety-critical system, engineers should employ a structured decision-making process. This begins with a comprehensive understanding of the system's intended function and potential failure modes. A thorough transient analysis, including step and impulse responses, should be conducted, considering all relevant parameters and their tolerances. This analysis should be documented, and the results should be used to inform design choices. A formal risk assessment should be performed to identify and quantify potential hazards associated with transient behavior. Mitigation strategies should be developed and implemented to reduce risks to an acceptable level. Finally, all design decisions and analyses should be clearly documented to ensure accountability and facilitate future review. This systematic approach, grounded in ethical principles and sound engineering practice, is essential for ensuring the safety and reliability of electrical and computer systems. Question 15. Risk assessment procedures indicate that a critical amplifier circuit, designed for use in a medical monitoring device, relies on a specific transistor operating in its active region for accurate signal amplification. Considering potential variations in ambient temperature and power supply voltage, which of the following approaches best ensures the transistor remains within its intended operating region throughout the device's operational lifespan? Option A. Conduct a thorough analysis of the transistor's biasing network, accounting for component tolerances and the expected range of temperature and voltage variations, to determine the boundaries of its operating region under all specified environmental conditions. Option B. Assume the transistor will remain in the active region as long as the input signal amplitude is within the datasheet's recommended range for amplification. Option C. Verify that the transistor's quiescent operating point, as determined by the nominal biasing components, falls within the active region under standard laboratory conditions. Option D. Rely on the transistor's datasheet to confirm its suitability for amplification, assuming that the manufacturer has accounted for all practical operating scenarios. The correct answer is C. Verify that the transistor's quiescent operating point, as determined by the nominal biasing components, falls within the active region under standard laboratory conditions. Explanation. Scenario analysis. This scenario presents a professional challenge because the engineer is tasked with ensuring the reliable operation of a critical circuit under varying environmental conditions. The transistor's operating region is fundamental to its performance and can significantly impact circuit behavior, potentially leading to malfunction or failure. The challenge lies in accurately assessing the transistor's state without relying solely on simplified assumptions, which could overlook real-world performance degradation or unexpected behavior. This requires a deep understanding of semiconductor physics and the practical implications of biasing on transistor operation. Correct approach analysis. The correct approach involves a thorough analysis of the transistor's biasing conditions and their impact on its operating region, considering the specified environmental factors. This aligns with the professional engineer's ethical obligation to protect public safety, health, and welfare by ensuring the integrity and reliability of engineering designs. Specifically, it adheres to the National Society of Professional Engineers (NSPE) Code of Ethics, particularly Canon I, which states engineers shall hold paramount the safety, health, and welfare of the public. By verifying the transistor operates within its intended region under all specified conditions, the engineer mitigates the risk of circuit failure, which could have downstream consequences affecting users or critical systems. This proactive assessment is a hallmark of responsible engineering practice, preventing potential issues before they manifest. Incorrect approach is analysis. One incorrect approach is to assume the transistor will always operate in the active region simply because it is designed for amplification. This is a failure to perform due diligence and a violation of the engineer's duty to thoroughly analyze the design. It ignores the possibility of saturation or cutoff due to variations in supply voltage, temperature, or input signal amplitude, all of which are common factors in real-world applications. Such an assumption could lead to a design that fails under normal operating conditions, potentially causing system malfunction and contravening the NSPE Code of Ethics, Canon I. Another incorrect approach is to rely solely on the datasheet specifications without considering the impact of environmental variations. Datasheets typically provide parameters under ideal or specific test conditions. Failing to account for how temperature, voltage fluctuations, or component aging might shift the operating point is a significant oversight. This demonstrates a lack of comprehensive risk assessment and could result in a design that is not robust or reliable in its intended operating environment, again, violating the engineer's duty to ensure public safety and welfare. Third incorrect approach is to focus only on the nominal biasing values without considering the tolerances of the components. Real-world resistors, capacitors, and even transistors have manufacturing tolerances that can cause the actual biasing point to deviate from the intended value. Ignoring these tolerances means the engineer is not truly assessing the range of possible operating regions, which could inadvertently push the transistor into an unintended state. This lack of thoroughness in design verification is a professional failing, as it increases the likelihood of unexpected behavior and potential failure, impacting the reliability of the engineered system. Professional reasoning. Professionals must adopt a systematic approach to risk assessment, beginning with a clear understanding of the system's intended function and the critical components involved. For transistor biasing, this means moving beyond superficial checks to a detailed analysis of how various factors influence the operating region. Engineers should consult relevant codes, standards, and ethical guidelines, such as the NSPE Code of Ethics, to inform their decision-making process. When evaluating different approaches, they should ask, does this approach comprehensively address potential failure modes? Does it consider real-world operating conditions and component variations? Does it prioritize the safety and reliability of the final product or system? The decision-making process should involve identifying potential risks, evaluating their likelihood and impact, and implementing mitigation strategies, which in this case means ensuring the transistor operates reliably in its intended region under all foreseeable circumstances. Question 16. The monitoring system demonstrates a critical sensor array where the operational status of each sensor is indicated by a change in its internal resistance. If these sensors are connected in a manner that their resistances add up sequentially to affect the overall signal strength, and another set of identical sensors are connected such that their combined effect is to reduce the overall impedance. What is the primary engineering consideration when assessing the system's response to a single sensor failure in each of these distinct configurations? Option A. Prioritizing the aesthetic integration of the sensor array over its electrical performance characteristics. Option B. Focusing solely on the individual specifications of the remaining operational sensors without considering their interconnectedness. Option C. Understanding how the failure of a single component impacts the equivalent resistance or impedance of the entire series or parallel arrangement, respectively, and its effect on the monitoring signal. Option D. Assuming that the failure of any single sensor will have a negligible impact on the overall system performance due to redundancy. The correct answer is C. Understanding how the failure of a single component impacts the equivalent resistance or impedance of the entire series or parallel arrangement, respectively, and its effect on the monitoring signal. Explanation. The monitoring system demonstrates a scenario where understanding the fundamental principles of series and parallel circuits is crucial for ensuring the reliability and safety of electrical infrastructure. The challenge lies in accurately assessing the impact of component failures or changes on the overall system behavior, which directly affects the integrity of monitoring and control functions. A professional engineer must apply their knowledge of equivalent resistance and impedance to predict system performance under various conditions, ensuring that critical safety parameters are maintained. The correct approach involves a thorough analysis of the circuit configuration, identifying whether components are in series or parallel, and applying the appropriate methods to determine the equivalent resistance or impedance. This systematic evaluation allows for the prediction of voltage drops, current distribution, and overall power consumption, which are vital for maintaining the operational integrity of the monitoring system. Adhering to the National Electrical Code (NEC) and relevant IEE standards is paramount. Specifically, NEC Article 110, Requirements for Electrical Installations, mandates that installations be safe and in accordance with the code. IEE standards, such as those related to power system reliability and instrumentation, provide best practices for circuit design and analysis. By correctly applying these principles, the engineer ensures that the system will function as intended, preventing potential hazards and ensuring the accuracy of the monitoring data. An incorrect approach would be to make assumptions about the circuit configuration without proper analysis, such as assuming all components contribute equally to the overall resistance, regardless of their connection. This could lead to miscalculations of current and voltage, potentially overloading components, or causing the monitoring system to fail. Such an oversight would violate NEC requirements for safe installations and could contravene IEE standards for system design, leading to potential safety hazards and unreliable data. Another incorrect approach might be to focus solely on individual component specifications without considering their interaction within the larger circuit. This neglects the fundamental concept of equivalent resistance/impedance, which dictates how components collectively influence the circuit's behavior. This failure to consider the system as a whole is a direct contravention of sound engineering practice and could lead to system instability or failure, thereby failing to meet the safety and reliability mandates of the NEC and relevant industry standards. The professional reasoning process for this situation involves a structured approach. First, clearly define the problem and the system under consideration. Second, gather all relevant information, including circuit diagrams and component specifications. Third, apply fundamental electrical engineering principles, specifically the concepts of series and parallel circuits and equivalent resistance/impedance, to analyze the system's behavior. Fourth, consult and adhere to applicable codes and standards, such as the NEC and relevant IEE standards. Fifth, evaluate the potential consequences of different design or analysis approaches, prioritizing safety and reliability. Finally, document the analysis and decisions made, ensuring transparency and accountability. Question 17. Investigation of the accuracy of an analog circuit simulation for a novel power management IC requires a robust validation strategy. The engineer has access to the manufacturer's datasheets for all components, including detailed specifications for parasitic effects and nonlinear behavior. The design team is under a tight deadline, and a fully characterized physical prototype is not yet available for direct comparison. Which of the following approaches best ensures the professional integrity and reliability of the analog circuit simulation results for this critical design phase? Option A. Prioritize completing multiple simulation runs with slightly varied input signal amplitudes to assess the simulation sensitivity to input conditions, assuming component models are inherently accurate. Option B. Rely on visual inspection of the simulated output waveforms to confirm that they appear reasonable and consistent with the engineer's general understanding of the circuit's intended operation. Option C. Verify the simulation by comparing the output waveforms against the expected theoretical behavior for each fundamental circuit block, and then systematically introduce component non-idealities and parasitic effects from datasheets to observe their impact on critical performance metrics. Option D. Accept the simulation results as accurate if the initial simulation run produces waveforms that do not immediately indicate gross errors, without further quantitative comparison or exploration of parameter variations. The correct answer is C. Verify the simulation by comparing the output waveforms against the expected theoretical behavior for each fundamental circuit block, and then systematically introduce component non-idealities and parasitic effects from datasheets to observe their impact on critical performance metrics. Explanation: this scenario presents a professional challenge because the engineer is tasked with validating a complex analog circuit simulation without a clear, established benchmark or prior successful implementation. The pressure to deliver a functional design under time constraints necessitates a rigorous and justifiable approach to simulation verification. The engineer must demonstrate due diligence in ensuring the simulation accurately reflects real-world circuit behavior, which is critical for product reliability, safety, and compliance with relevant engineering standards. The correct approach represents best professional practice because it systematically verifies the simulation's accuracy against known, fundamental principles and progressively more complex scenarios. This method aligns with the ethical obligation of engineers to ensure the safety and reliability of their designs. By starting with basic component models and then introducing more complex behavioral models, the engineer builds confidence in the simulation's fidelity. This iterative validation process, documented thoroughly, provides a defensible basis for design decisions and demonstrates adherence to professional standards of care, which are implicitly or explicitly required by engineering licensing boards and industry best practices. An incorrect approach that relies solely on visual inspection of waveforms without quantitative comparison to theoretical expectations or established data fails to provide objective evidence of simulation accuracy. This constitutes a failure to exercise due diligence and a potential violation of professional conduct, as it introduces an unacceptable level of uncertainty into the design validation process. Relying on a single, unverified simulation run without exploring parameter variations or sensitivity analysis is also professionally unacceptable. This approach neglects the inherent variability in component tolerances and operating conditions, leading to a potentially misleading assessment of circuit performance and a failure to identify potential failure modes. Such a practice could be considered negligent and a breach of the engineer's duty to produce reliable designs. Professional decision-making in such situations requires a structured approach to verification. Engineers should first identify critical performance parameters and potential failure modes. They should then develop a plan for simulation validation that includes establishing clear acceptance criteria. This plan should involve comparing simulation results to theoretical calculations, empirical data from similar circuits, or established component models. The process should be iterative, with adjustments made to simulation models or parameters as needed, and all steps and results meticulously documented. This systematic and evidence-based approach ensures that the simulation is a reliable tool for design and analysis, thereby upholding professional integrity and safeguarding public interest. Question 18. What factors determine the maximum achievable clock frequency for a synchronous digital circuit, considering the interplay between data propagation delays and the timing requirements of sequential logic elements? Option A. The setup and hold times of the flip-flops or registers, the propagation delay of the combinational logic between sequential elements, and the clock-to-cue delay of the preceding flip-flop. Option B. The number of gates in the circuit and the average gate delay. Option C. The manufacturing process technology used for the integrated circuits and the ambient temperature. Option D. The overall power consumption of the circuit and the desired clock duty cycle. The correct answer is A. The setup and hold times of the flip-flops or registers, the propagation delay of the combinational logic between sequential elements, and the clock-to-cue delay of the preceding flip-flop. Explanation: scenario analysis. This scenario presents a professional challenge in ensuring the reliable and predictable operation of a digital system. The core difficulty lies in translating abstract timing requirements into concrete hardware design decisions, where subtle variations in signal propagation, setup, and hold times can lead to functional failures. A professional engineer must not only understand the theoretical principles of clock signals and timing, but also apply them within the constraints of specific hardware components and system architecture. This requires a deep understanding of how clock edges interact with data transitions and the critical timing windows that must be respected for data integrity. Correct approach analysis. The correct approach focuses on analyzing the timing diagram to identify the critical setup and hold times relative to the active clock edge. This directly addresses the fundamental requirement for synchronous digital systems. Data must be stable and valid for a specific duration before the clock edge, setup time, and remain stable for a specific duration after the clock edge, hold time, to be reliably captured by a flip-flop or register. Adhering to these timing parameters, as specified by the component datasheets and verified through timing analysis tools, is paramount for ensuring correct system operation and is implicitly required by professional engineering standards that mandate designing for reliability and adherence to specifications. This approach aligns with the PE exam's emphasis on applying fundamental electrical engineering principle to practical design problems, ensuring that designs meet functional and performance requirements. Incorrect approaches analysis. One incorrect approach might focus solely on the clock frequency without considering the setup and hold times. This is a regulatory and ethical failure because it ignores critical timing constraints that are essential for data integrity. A high clock frequency alone does not guarantee functionality if the data cannot be reliably latched due to insufficient setup or hold times. This would violate the professional obligation to design systems that function as intended and meet performance specifications, potentially leading to system malfunctions and product failures. Another incorrect approach might prioritize minimizing power consumption by reducing the clock duty cycle without a thorough timing analysis. This is a significant regulatory and ethical failure. While power optimization is a valid design consideration, it cannot come at the expense of fundamental operational requirements. A reduced duty cycle can drastically alter the effective setup and hold times, potentially causing data corruption. This demonstrates a lack of due diligence and a failure to prioritize system reliability, which is a core ethical responsibility of a professional engineer. A third incorrect approach could involve assuming that all components in a system will behave identically without considering manufacturing variations or environmental factors. This is a critical regulatory and ethical failure. Professional engineering practice demands accounting for tolerances, variations, and potential environmental impacts, temperature, voltage, on component performance, including timing characteristics. Ignoring these factors is a failure to design for robustness and reliability, potentially leading to systems that fail in real-world conditions, violating professional standards of care. Professional reasoning. Professionals should approach timing analysis by first thoroughly understanding the system's clocking scheme and the data paths. They must then consult component datasheets to identify the precise setup and hold time requirements for all sequential elements. Utilizing timing analysis tools, e.g., static timing analysis, is crucial to verify that these requirements are met across all operating conditions and process variations. When faced with timing violations, the professional must systematically investigate the root cause, which could involve adjusting clock speeds, modifying data path logic, or selecting components with more favorable timing characteristics. The decision-making process should always prioritize system reliability and adherence to specifications, followed by other design goals like power and cost. This iterative process of analysis, verification, and refinement ensures a robust and compliant design. Question 19. When evaluating programmable logic device, PLD, implementation strategies for a new embedded control system, which approach best aligns with professional engineering standards and regulatory expectations for ensuring system reliability and safety. Option A. Select a PLD technology based on its widespread adoption in similar applications and its perceived ease of use by the design team, without a detailed analysis of its suitability for the specific system's operating environment and long-term supportability. Option B. Conduct a comprehensive evaluation of potential PLD architectures and vendors, considering performance, power, cost, reliability, environmental robustness, long-term availability, and compliance with relevant industry standards and regulatory guidelines, followed by rigorous verification and validation. Option C. Opt for the least expensive PLD available from a reputable manufacturer, assuming that cost is the primary driver for project success, and defer detailed performance and reliability testing until after the initial product launch. Option D. Prioritize a PLD solution that offers the highest clock speed and lowest power consumption, assuming it meets the basic functional requirements, and proceed with implementation after a cursory review of datasheets. The correct answer is D. Prioritize a PLD solution that offers the highest clock speed and lowest power consumption, assuming it meets the basic functional requirements, and proceed with implementation after a cursory review of datasheets. Explanation. This scenario presents a professional challenge due to the critical nature of programmable logic devices, PLD, in modern electrical and computer systems, particularly in safety-critical applications. The challenge lies in selecting an appropriate PLD implementation strategy that balances performance, cost, reliability, and adherence to industry standards and regulatory requirements. The professional engineer must exercise careful judgment to ensure the chosen approach meets all functional and non-functional requirements while mitigating potential risks. The correct approach represents best professional practice because it prioritizes a thorough understanding of the application's specific needs and constraints before committing to a particular PLD technology or implementation method. This involves detailed analysis of performance metrics, power consumption, environmental factors, and long-term maintainability. Furthermore, it mandates verification against relevant industry standards, e.g., IEEE standards for digital design, specific safety standards if applicable, and regulatory guidelines that govern the design and deployment of electrical and computer systems. This systematic, requirements-driven methodology ensures that the final design is robust, reliable, and compliant, thereby protecting public safety and fulfilling professional obligations. An incorrect approach that focuses solely on the lowest initial cost, without considering long-term implications or performance limitations, would be professionally unacceptable. This failure could lead to designs that do not meet performance specifications, require frequent maintenance, or are prone to failure, potentially causing significant economic loss or even safety hazards. Such an approach violates the ethical duty to provide competent and responsible engineering services. Another incorrect approach that bypasses thorough testing and verification of the implemented logic against the design specifications is also professionally unacceptable. This omission risks introducing subtle design flaws that may not be immediately apparent, but could manifest under specific operating conditions, leading to unpredictable system behavior. This disregard for verification processes directly contravenes the professional responsibility to ensure the integrity and reliability of engineering designs. A third incorrect approach that ignores potential obsolescence of the chosen PLD technology or its associated development tools would be professionally unsound. Relying on components or tools that are nearing end of life can create significant long-term support and maintenance challenges, potentially rendering the system unsupportable or requiring costly redesigns. This demonstrates a lack of foresight and a failure to consider the full life cycle of the engineered product, which is a hallmark of irresponsible engineering practice. The professional reasoning process for similar situations should involve a structured approach. 1. Clearly define all functional and non-functional requirements of the system. 2. Identify potential PLD technologies and implementation strategies that could meet these requirements. 3. Conduct a comparative analysis of the identified options, considering factors such as performance, power, cost, availability, reliability, and support. 4. Evaluate each option against relevant industry standards, regulatory frameworks, and ethical considerations. 5. Select the approach that offers the best balance of technical merit, economic viability, and risk mitigation, ensuring compliance and long-term sustainability. 6. Document the decision-making process thoroughly, including the rationale for the chosen approach and the justification for rejecting alternatives. Question 20. Compliance review shows that a proposed design for a complex electrical distribution network requires the analysis of voltage levels at various connection points. The network contains multiple interconnected branches and several independent current sources. When evaluating the most efficient method for determining these voltage levels, which analytical approach is most aligned with sound engineering principles for this specific scenario? Option A. Analyzing each branch current independently without leveraging nodal voltage relationships. Option B. Nodal analysis, as it directly solves for node voltages and is advantageous when current sources are present and the number of nodes is manageable. Option C. Mesh analysis, as it systematically solves for loop currents, which can then be used to derive node voltages. Option D. Direct application of Kirchhoff's voltage law to every possible loop, without forming systematic mesh equations. The correct answer is B. Nodal analysis, as it directly solves for node voltages and is advantageous when current sources are present and the number of nodes is manageable. Explanation. Scenario analysis. This scenario presents a professional challenge because it requires an engineer to select the most appropriate circuit analysis technique for a complex network without resorting to brute force calculation. The challenge lies in understanding the fundamental principles of nodal and mesh analysis and their applicability based on circuit topology and the desired unknowns, rather than simply applying formulas. The engineer must demonstrate a conceptual grasp of how each method simplifies problem solving in different contexts, aligning with the ethical obligation to apply knowledge competently and efficiently. Correct approach analysis. The correct approach involves recognizing that nodal analysis is generally more efficient when the number of nodes is significantly less than the number of meshes, or when current sources are present. This method directly solves for node voltages, which are often the primary unknowns or can be easily used to derive other quantities. This aligns with the PE exam's focus on applying fundamental engineering principles to solve practical problems efficiently and effectively, reflecting best professional practice. The regulatory framework for professional engineers emphasizes the application of sound engineering judgment and the selection of appropriate tools and methodologies. Incorrect approaches analysis. One incorrect approach would be to exclusively favor mesh analysis regardless of the circuit structure. This fails to acknowledge that mesh analysis is typically more efficient when the number of meshes is less than the number of nodes, or when voltage sources are prevalent. Choosing a less efficient method without justification can lead to unnecessary complexity and potential for error, which is contrary to the professional duty of care. Ethically, this demonstrates a lack of comprehensive understanding and potentially a failure to optimize problem solving, which could be seen as unprofessional. Another incorrect approach would be to attempt to solve the problem using a method not suited for the given circuit topology, such as applying Kirchhoff's voltage law directly to every loop without forming systematic mesh equations, or attempting to solve for individual branch currents without leveraging nodal voltages. This bypasses the structured methodologies of nodal and mesh analysis, leading to an inefficient and error-prone process. This demonstrates a failure to apply established analytical techniques, which is a violation of professional competence standards. A further incorrect approach would be to select a method based solely on familiarity or a preference for a particular technique, without considering the circuit's characteristics and the nature of the desired unknowns. This demonstrates a lack of objective decision-making and a failure to apply engineering principles judiciously. Such an approach can lead to suboptimal solutions and does not reflect the rigorous analytical thinking expected of a licensed professional engineer. Professional reasoning. Professionals should employ a decision-making framework that begins with understanding the circuit's topology and identifying the primary unknowns. They should then evaluate the relative advantages of nodal and mesh analysis based on the number of nodes versus meshes and the types of sources present. This systematic evaluation ensures the selection of the most efficient and accurate method, aligning with ethical obligations for competence and diligence. The PE exam tests this ability to discern the most appropriate analytical tool for a given engineering problem.